You know that chart from your high school chemistry class? Well, it's so much more than just a list of elements. It's really a map of the entire universe, kind of a cheat sheet for matter itself. Today, we're going to decode the logic and the incredible story behind the periodic table. Okay, let's crack this thing open.
Nobel laureate Glenn Seaborg absolutely nailed it. The table's real power is that it shows us a hidden order. It tells us that the building blocks of, well, everything, aren't just a random jumble. They belong together in families, and they follow a secret set of rules. And our job today is to figure out what those rules are.
So let's rewind the clock. Picture this. It's the year 1800. Scientists only knew about 31 elements. That's a pretty manageable number, right? You could list them, maybe memorize a few properties. But as you know, science never really stands still.
Now fast forward to today, and boom, we're at 118 known elements, and scientists are still creating more in labs. The problem becomes kind of obvious. How in the world do you manage this explosion of information? A simple list just isn't going to cut it anymore.
I mean, this was the fundamental challenge. This is so much bigger than just making a tidy chart. It's about finding the underlying logic of matter itself. And this very question kicked off a quest for order that would completely change chemistry forever.
So the first attempts to find this order, well, they were like trying to tune in a faint radio signal through a whole lot of static. They weren't perfect, not by a long shot, but they were absolutely crucial because they proved that a pattern was actually there to be found.
First up, in 1829, you had Dobereiner, who found these little groups of three he called triads, where one element was basically a mix of the other two. Then you have de Chancretois, who put the elements on a cylinder and saw that properties started lining up. And in 1865, John Newlands noticed a pattern repeating every 8 elements, kind of like a musical scale. All these scientists were sniffing around the right idea. They just hadn't quite seen the whole picture yet.
And that brings us to the hero of our story, the Russian chemist Dmitry Mendeleev. See, he didn't just organize the elements he knew about. No, he created a system so powerful it could actually predict elements that no one had ever even seen before.
This right here was Mendeleev's guiding light. His big idea was that if you line up the elements by their atomic weight, their properties will start to repeat in a predictable, periodic pattern. For him, the chemical properties, how an element behaves, that was the most important clue in the whole puzzle.
Okay, this is where his absolute genius really shines. When an element didn't seem to fit his pattern based on its weight, he didn't just throw his hands up and say his theory was wrong. He had the incredible confidence to say, no, the weight is wrong. Or even more boldly, there's an element missing here. He literally left gaps in his table, just trusting that one day they'd be filled.
And check this out. This is the proof, the reason he became legendary. He didn't just leave a blank spot under aluminum, he predicted, with stunning accuracy, the properties of this missing element he called Eka aluminum. And just look at how ridiculously close he was. When gallium was discovered in 1875, it was a near-perfect match. This turned his table from just a chart into a legitimate predictive machine.
But, like in any great story, there was a twist. As brilliant as Mendeleev's table was, its foundation, atomic weight, had a few, well, let's call them glitches. It took a totally new discovery to provide the final, fundamental upgrade and reveal the true principle that was really at work. In 1913, a physicist named Henry Moseley was working with X-rays, and he found that the true, unique fingerprint of an element wasn't its weight at all. It was its atomic number, which is just the number of protons in its nucleus. This was it. This was the fundamental property that Mendeleev's table was hinting at all along.
So this is the crucial upgrade, right? Mendeleev's table was based on a pattern he could see, an observation, which was absolutely brilliant. But Moseley's discovery gave us the why. Organizing by the atomic number, by the proton count, fixed all the little inconsistencies in the old table. It was the true source code of the elements.
And this brings us to the law that governs the periodic table we all use today. It's a really subtle change in the wording, but it represents a monumental shift in our understanding. The entire shape and structure of the table is a direct result of this one fundamental principle.
All right, so with this modern law in our back pocket, we can finally understand why the table is shaped the way it is. The best way to think about it is not as some random grid, but as a city with distinct neighborhoods where each one has its own unique character.
So in this city, you've got two main directions. The horizontal rows are called periods. Think of them like floors in a building. As you go down a floor, you're adding new energy levels or shells for the electrons. The vertical columns are the groups. Think of these as families. Everyone living in the same column has a similar outer electron setup, which means they all have very similar chemical personalities.
And what about that kind of strange shape? Well, it's not random at all. It's literally a map of how electrons fill up their available living spaces, which we call orbitals. The layout follows a super strict order, starting with the s orbitals, then the p, d, and f. This structure isn't just for looks, it's a visual guide to quantum mechanics. Over on the far left of our map, we have the S-block neighborhood. These are the alkali and alkaline earth metals, and these guys are highly reactive because they're just dying to give away their outer electrons to become more stable. They're the oversharers of the elemental world.
Now from those electron givers, let's zip all the way across town to the right side. This is the P block, and it's by far the most diverse neighborhood. You've got everything here. Metals like aluminum, nonmetals like carbon, the superreactive halogens, and you end with the noble gases, the cool kids who are so stable they don't react with anyone. And connecting these two very different sides, right in the middle of the table is the D block. These are the transition metals. Think iron, copper, gold. They're the workhorses, known for being strong and for forming really colorful compounds. Their secret is that they can share different numbers of electrons, which makes them fantastic catalysts for chemical reactions.
And finally, what about those two rows that always seem to be floating at the bottom? That's the F block, the inner transition metals. They're just pulled out to keep the main table from being ridiculously wide. This neighborhood is home to many radioactive and even man-made elements.
So we've gone on this journey from a simple list of 31 elements to this elegant, logical, and incredibly powerful scientific tool. But here's the thing, the quest for understanding is definitely not over. If you take away one thing, let it be this. The periodic table is not a static document. It's a living map that brought order from chaos. And its real power isn't just in organizing what we already know, but in giving us a framework to predict the properties of elements that don't even exist yet. And that leaves us with a pretty fascinating thought to end on. The seventh row of the table, the seventh floor, is now complete. But using the exact same logic we've talked about today, scientists are already predicting the properties of element 119, 120, and on and on. The map isn't finished. There are still whole new territories out there waiting to be discovered.